Hi folks, Astronomy Live here. Today I'm going to be talking a bit about how I film footage like this using my RocketTraker software, and about the latest release of RocketTraker that I've just published and made available for download by all channel members. So if you're a channel member, go check the community tab. The link to the latest compiled executable is now available for download. As well as the compiled executable, RocketTraker is indeed open source software, and you can also find a link to the source code on my GitHub page in the video description as well. We have quite a few new subscribers thanks to that Starship video, so if you're new here, welcome. RocketTraker is software that I developed specifically for tracking rocket launches with off-the-shelf telescope hardware like the 11-inch Celestron NexStar that I used for Starship. It allows me to use a joystick to directly control the telescope's motion, but it also allows me to download the flight trajectory from flightclub.io and load that into the program so that the telescope will automatically follow the predicted path of the rocket. You can then correct for any deviations in pointing either with the joystick or with a video viewfinder to optically track the rocket. So let's take a closer look at the program now, and let me show you the latest features of RocketTraker for anyone interested in filming launches like this. Welcome to RocketTraker Beta version 14.0. Now, I'm going to first cover the latest features of RocketTraker for current users of the program, but then we're going to go into a tutorial on how to use RocketTraker for people who might be new to the program so that you can get the most out of it. One of the newest features is this planetarium feature, so that when you load a trajectory from Flight Club, it will project the path of the rocket as a yellow line over the sky as it will be at the T0 time that you currently have selected. So, as usual, you can click a launch from the upcoming launch list that is updated when you first launch the program, and it will update the T0 time, and then you can load your trajectory from Flight Club, and it will show you the path of the rocket at that T0 time. Now, in addition to simply showing you the path of the trajectory, we can also go into a mapping feature and see where the trajectory is on the current sky with the stars and planets in their current position. So we also have the ability to map out the pointing error of the telescope along that trajectory in order to achieve even higher levels of precision. So first I'm going to connect to my telescope, and I'm going to do that in this case with CPWI. So this is another new feature, is compatibility with CPWI. Previous versions of the program required you to use NextRemote, but NextRemote is not compatible with the latest computers. If you buy a Windows 11 computer now, chances are NextRemote will not work with it, so you'll need to migrate to CPWI, which is a newer program. So now we have compatibility with CPWI, which is quite nice. The pointing error mapping feature is a bit redundant if you are actually using CPWI, but if you're still on NextRemote or using another kind of telescope, this can still be quite useful. So we can see here the projected path of the rocket's trajectory that I've loaded from Flight Club, and we can see the stars as they currently are in relation to that trajectory through the sky. So we want to pick some stars that are close to that trajectory, slew to them, center them up in the main telescope, and then sync on their positions within RocketTraker. So I'm going to go ahead and click on Polaris here. We can see this brings up some information. Alpha Ursa Minor, that is the name for Polaris. We can see its altitude, azimuth, magnitude, and we can slew to it. Also, very importantly, we have a new feature that allows us to abort any given slew, whether that is related to camera calibration or slewing to a target for a launch if you're using slew horizon and wait mode, or in this case, slewing to a star to sync on its position. So I'm going to go ahead and click slew. Starts the slew, and if I hit abort slew, it immediately stops the telescope in its tracks. So if you don't like what the telescope is doing, you can stop it at any time with the abort slew button either here or on the main window. We also have an abort slew button over here, which is handy if you're using that camera calibration feature and it's moving further than you'd like, or you're not liking what you're seeing with a cable, what have you. You can abort the slew at any time. Either button will do the same thing. So let's go ahead and resume the slew back to Polaris. Obviously I'm doing this indoors right now for testing purposes, but obviously you would want to be doing this with actual stars to sync the position accurately. Okay, so we've slewed to Polaris. Now let's say that we have synced on Polaris. We've actually lined it up. Let's go ahead and sync on Polaris. And it will record the current offset of where the telescope thought it was versus where you told it the star actually was. So I'm going to go ahead and pause the all-sky view, which you should always do when shutting down this planetarium window, and then look at the pointing error list. So we have one mark that is close to the altitude and azimuth that was expected for Polaris, and you can see that it's reported altitude and azimuth there in degrees. And so you can do this for multiple stars, and it will build up a map of pointing errors and interpolate between those points in order to correct the telescope's pointing and achieve the best possible accuracy when following a given prediction. So we also have some more features that can be bound to the joystick. So I don't believe I had this in the last version that I publicly released, but we have now a prediction lock feature, which you can bind to a joystick button, or if you're using a gamepad, you can bind it to a gamepad button. And if you push that button, it will send the telescope to be as close as possible to the current predicted altitude and azimuth from the Flight Club file. So it will follow that file as precisely as possible, look at where the telescope's reporting its position, and then adjust the tracking to minimize the error from that position, including any mapping that you may have done of stars along the rocket's path. So that's handy, especially if you're doing a slew to horizon and wait. If you're trying to, say, track Starship from Florida during the day when you can't see it visually and you're trying to get it in the telescope's view, you can use prediction lock to ensure that you're as close as possible to the predicted position, and hopefully Starship will follow the nominal trajectory. If it doesn't, you can disengage prediction lock by pushing that same button again, and you will have control with the joysticks once again. So when you're in prediction lock mode, the joysticks won't do anything because the program is doing everything it can to keep the telescope as close as possible to the exact predicted position of the rocket. So let's take a look at how that works. So I'm going to go ahead and do a slew to horizon and wait. Now I'm going to hold at a position 10 degrees above the horizon and wait for the rocket to hit that point. I'm going to arm for launch tracking and go ahead and manually trigger that launch, and it will slew to that position 10 degrees above where it expects the rocket to rise. It won't take very long to get there either, because this is a trajectory for a very local launch. So you can see the countdown to hitting that point is only 15 seconds. So I'm going to go ahead and manually trigger it to begin tracking, and then use prediction lock, and it will slew down towards where it had expected that rocket to be and continue to follow it back up. So you can see the as diff, the out diff. This is distance from the exact predicted position. So I'm going to go ahead and override that launch and stop the telescope, and then stop joystick tracking. So once again, if you weren't already familiar with it, there are bindings as well for manually starting the launch and reverting to full manual tracking. So if you push revert to full manual tracking, it will send it back into the normal start joystick tracking feature where there is no prediction. It's just going based on your inputs on the joystick. If you don't like what the prediction is doing, if the rocket is off of the nominal trajectory or it's fighting you, you can override that with revert to full manual tracking, and then that puts you into the same mode as if you'd clicked start joystick tracking, where you have joystick control, and then once you're done with that, you can click stop joystick tracking to disable the joystick and return to normal. So those are the main new features, and again, as I said, the abort slew feature will also work when doing camera calibration. So let's say I want to calibrate using this feature right here, and I do a camera calibration, I can abort at any time with the abort slew button. Now it's still looking for the camera calibration to be completed, so you can go ahead and just click somewhere else and force it into thinking, oh, now I know the image scale. Just click somewhere else in the image and it will finish its calculation, even though that number is really wrong. So we can just do it again, camera calibration, and now it has figured out the image scale in reality because I aborted the first attempt. So if for some reason it doesn't stop, it should, but if for some reason it keeps going when it's finished with calibration, you can abort it with the abort slew. That was a bug in previous versions for some users, especially if you were using CPWI. It was actually overloading CPWI with too many movement commands, and so that was queuing up and continuing to move the scope even after it had stopped sending commands. So if something like that were to happen again, you can abort the slew, but that bug is now fixed and shouldn't occur again. So now that I've calibrated, if I click on something, initially nothing will happen, but if I click Start Joystick Tracking, it will also enable video-based tracking and go to that point. So now we can do video-based tracking as well. So that's all there is to that. So again, these are the main new features of the program. So now I'm going to give a more general tutorial for people who are new to the program, maybe never used it before. For those of you who are still waiting on remote joystick tracking, let me know. This requires a separate program to be able to set up a server-client relationship and be able to control RocketTraker from a different computer over the internet. The remote joystick program still needs to be updated to incorporate the ability to bind buttons for the latest features. So I haven't updated that yet, but that will be coming as well. Alright, so now let's get into a tutorial for how to use RocketTraker. Alright, so here's a tutorial on the basics for those of you new to the program. Essentially, the first step is going to be to start your camera, which RocketTraker uses anything that Windows recognizes as a video camera. So you want to get just a basic USB camera, or you could use a USB dongle that grabs a standard definition or even an HDMI video feed and incorporates that into Windows as a video camera. I like to use either an ELP camera that you can get off of Amazon, or sometimes I'll use a standard box security camera which has even better sensitivity for tracking objects at night. And then I'll use a RCA or component video capture dongle with USB to bring it into RocketTraker. So the next thing you want to do is make sure that the center point and crosshair are co-aligned with the main telescope. The center point is represented by a red box, and that's where the program will try to drive any object that you click on. The crosshair is a purple circle around the red box. Those can be at two different points. The purple circle of the crosshair is just there for your reference. It doesn't affect the pointing of the telescope. The red box is where the program will actually try to drive the target if you click on it for video viewfinder tracking. So with your main telescope pointed at an object that you can see in the viewfinder, you want to click Set Center Point and then click on that object to co-align it. Then you can click Reset Crosshair and that will bring the purple circle to the same point. You can also move the red box pixel by pixel with the arrow keys on your keyboard. And you can even do this while tracking, which is helpful if the target is lagging ahead or behind of where the crosshair is. You can drag it into the purple circle by moving the red box to bring the object into frame, using the arrow keys while you're tracking the object. Then you want to connect the scope. So again, you want to select your telescope type. These newest features are specific for ASCOM Alt-Az, but I will be porting it to LX200 AutoStar as well. LX200 Classic has a more limited command set, so it's not able to do predictive tracking, at least at the current time. It's more limited to just video and joystick-based tracking. So I've selected to ASCOM Alt-Az, so then you can click Connect Scope and pick your scope type from the drop-down list with the ASCOM pop-up. I'm selecting CPWI and then clicking OK. It now reports the maximum slew rate for the scope. Now with CPWI, this is a limitation of CPWI itself, that it reports to my program that the maximum slew rate of the scope is 3 degrees per second. Now in reality, I know for a fact this scope can do 4 degrees per second at maximum. However, CPWI is more conservative and tells all external programs, no, the scope can only do 3 degrees per second, so now my program has to respect that conservative limit set by CPWI. So that's just something that we just have to deal with. I haven't found a way to override that with CPWI as of yet. So then the next step in your setup process would normally be to perhaps calibrate the video camera. Now, for those who are new to RocketTraker, RocketTraker, because of how it works, it does require some video camera to be running at the time. It could be your laptop's internal camera, maybe not even really on the scope, and you could just use it as a dummy. That's fine, but it does require a video camera because it's looking for the timing of those video frames coming down in order to do all of its calculations for anything that might be tracked, or to be able to potentially track objects with a video camera so that it can determine the motion of that object in degrees per second and send the telescope to that object. So now that the camera's running, you can click on any feature, and again you can use either feature-based tracking, which detects features like the letter S here, or you can do brightness-based tracking, which is just going to go to the brightest thing it can see. And I'm going to use feature-based tracking in this case, and I'm just going to click on an object and then click camera calibration. Now you can set the calibration speed that's up here in the top right in degrees per second. 2 degrees per second is a good number. It's fast enough without completely maxing out the scope. So I click camera calibration. It's going to move that target until it moves about 100 pixels, and then determine what the pixel scale is. So it determines that scale to be about 0.068 degrees per pixel. So now that's completed. You want to make sure you've got your joystick plugged in. In fact, you want to make sure you've plugged in your joystick before you launch RocketTraker, because it only polls for any connected joysticks or gamepads at the time that it launches the program. So if you've connected your gamepad or your joystick after you launched RocketTraker, you're going to need to disconnect the scope, stop the camera, file, exit, and save configuration so that it remembers your configuration, and then relaunch the program. But in this case, I've already got the joystick connected, so we're good to go. So again, I'm going to start camera, connect the scope once again, and we're good to go. So again, as I previously demonstrated, at this point, because we're calibrated, I can simply click Start Joystick Tracking, and it will start tracking anything I click on. Just like so. Easy enough. So I'm going to go ahead and stop joystick tracking. So that's how basic joystick and video-based tracking functions. You also want to set your location. I've just set a dummy location here, but this is going to be very important for things like mapping out the pointing error of the telescope. It's going to salute to the stars, and then it's going to measure their positions based on your location in altitude azimuth coordinates. So you want to make sure that that is accurately set, not only in, say, CPWI in this case, but also here in RocketTraker as well. As for the COM port number, you can ignore this. This is only used for the ALX200 Classic. If you're on an ALX200 Classic and trying to connect to the scope, you need to set your COM port number here. If you're on ASCOM, then you can ignore this. This is not really used. The camera number, we normally start at 700. You can start at camera index 0. In Python, most indices start at 0, and it will essentially should do the same thing. Now in this case, it's actually walking up pretty good here, but it should theoretically fire up the camera, or at least it's going to try to. But it may just straight lock up the program, so be advised. Normally you want to start at index 700 and iterate up from there. If it's not the correct camera, go to 701, go to 702, 703, so on and so forth. I gave it a second, and it actually finally did start the camera, but it's much slower. I'm not quite sure why that is. It's got something to do with Python and the way OpenCV works and how it interacts with the camera, but it seems to give a more direct connection to the camera if you choose index 700 as opposed to index 0. Don't ask me why. That's something about the way that Windows works with OpenCV/Python. OpenCV is the open source computer vision library used by Python for interacting with these images. So I've selected 700 because this is the only camera I currently have connected to this computer. If I were on a laptop with a built-in webcam, that webcam usually takes over index 700, and then any external camera would start at 701. The next thing would be to know if you're going to do a predictive tracking of the rocket. If you're going to perform slew to horizon in wait mode, this is a mode specifically developed for tracking Starship from Florida when it's launching from Texas, but it would work for tracking any given rocket from a distant location where you're expecting to come up over the horizon. You can set a horizon altitude limit that it will slew to, and it'll look for the earliest point in that trajectory file that is at least that high, and then slew to those coordinates at the start, waiting for it to rise over, say, the current tree line or roof line. So you'll need to sort of determine that yourself, or at least take an educated guess at it, and then put it in here to be able to set your altitude limit for that slew to horizon in wait mode. And then you can update the horizon altitude for that mode. So if you are going to be doing any kind of predictive tracking, you'll need to load the trajectory file. You can get these trajectory files from flightclub.io from their altitude azimuth download page. So here's Flight Club. So I've gone ahead and selected my location, and then let's go ahead and just pick a mission. So let's say Crew 10, and it will pull up the trajectory. So you can download the path as a CSV file that will be loaded into my program to serve as the prediction. So again, that is from DataViz, Alt As Generator. You come in here, and then you can select your location and select the trajectory that you wish to download. So now back in RocketTraker, let's pick a tracking mode. So we'll try regular predictive tracking. And the way that this works is that when you want to track the launch, the first thing you need to do for regular predictive tracking is manually center up on the launch pad. So normally I use joystick for tracking for this. I'll just take the joystick and move the telescope until I find the launch pad and center up on it. So let's just say this spot right here is the launch pad. So I stop joystick tracking there and make sure I've selected regular predictive tracking. So now when I arm for launch, and let me just pick a launch I know is in the future, it's going to count down. As you can see, it shows you the T-minus count, and you can either choose to use the computer clock, in which case you can check use countdown clock, and it will actually use this to trigger the launch. When this hits T0, it will automatically start playing back the prediction. The other thing it's going to do when launch occurs is it will sync the telescope's coordinates on the pad location. So it will look at where the telescope was at liftoff, and it will assume that you were pointed at the launch pad. That's only true of regular predictive and adaptive predictive tracking modes. Slew to horizon and wait mode, of course, does not assume that at all. It simply slews directly to the coordinates it expects the rocket to rise at. So it relies on you to align the telescope as accurately as possible, which again is why that pointing mapping feature is so important. But for regular predictive or adaptive predictive, these are modes that are typically used when you're close enough to the launch site to see the rocket on the pad, and it assumes that you have pointed the telescope at the rocket on the pad at liftoff. So you can either choose to use the countdown clock, or if you uncheck this button, it will rely on you pushing the joystick button that you have bound to manually start the launch, which you can do at any time. You can wait till after the predicted T0 time, or you can fire it even before the predicted T0 time, and it will initiate the launch. So I'm going to go ahead and push the button now, and it will immediately start playing back the trajectory file. You can see the rates changing rapidly here as it slowly plays back the launch file in real time. We can see the T+ time is now going up, and we have full joystick control as well, so I can adjust with the joystick if the rocket is moving differently than the prediction, and I can go back to the prediction as well. Let's say I move it way off here. I can go back to the prediction as well with the prediction lock feature. So if I push that button, it automatically goes right back to where it expects the rocket to be. So I can then override and go to full joystick tracking and stop it myself. And again, you can arm and disarm at will, but if you use countdown clock, it will rely on the computer clock to start. You can also record the video viewfinder with the record video button, and you can reverse the X and Y axes of the telescope as desired. So those are the basic features of RocketTraker. We also have a few ancillary features like image orientation. You can rotate the viewfinder image if your camera is slung underneath the telescope and upside down, or you can fix that with the rotate 0 degrees. You can vertically flip the image if you're looking through, say, another telescope as your finder, and if that image orientation is flipped by the telescope, you can undo that with the vertical flip feature or the horizontal flip feature, or return to normal orientation with the normal orientation view. Now this program does assume that the view is orthogonal, that up is up, down is down, left is left, right is right. So you want to make sure that the actual image orientation that you're seeing corresponds with the way the telescope moves when you, say, engage joystick tracking and move it left and right. Again, we also had feature-based tracking, which can be useful for, say, a daytime launch where you have a white cloud. Maybe it's a rocket with some solid rocket boosters on the side, and it's emitting a lot of white smoke behind it. White smoke might be quite bright and confuse brightness-based tracking. So feature-based tracking might be more useful in those cases if you're trying to track the tip of that smoke trail where the rocket is. And that's pretty much it. We also have refraction options, so you can set the current temperature and pressure to correctly calculate for refraction. Again, important when doing mapping of the stars and mapping of the pointing error of the telescope. You can also do window scaling, so you can set the image-based scaling factor. So this is designed to resize the whole window for RocketTraker based on how big the camera image is that comes in. It will rescale that to fit so that it doesn't exceed the size of your screen. So if you're having issues with that, you can go in here and change this setting to be able to fix that. And then we have spiral search. So you can set a spiral search radius, and it will spiral out and it'll keep adding to that radius by this amount every circle that it does. Spiral search can be handy if you're, again, trying to track a rocket during the day using slew to horizon wait mode and you don't know precisely where it is. And then there's configure focuser. So I'm working on adding ASCOM focuser compatibility, but it's not quite there yet, so this is still an experimental, mostly broken feature. I have my own personal focuser that I've built and developed myself, but that's just my own hardware that I connect to. So everyone else is going to want to be using the ASCOM focuser capability, but it's not quite finished yet, so that's for a future update. And that's pretty much it. So when you're done, you want to disconnect the scope, stop the camera, and then to exit and save configuration, you want to go to File, Exit, and Save Configuration. That'll save your settings, including your location, your camera number, your COM port, all that kind of information. If you don't want to save the settings, just close out of the program with the X, and it will not update the configuration file. And that's pretty much it for RocketTraker. So if you have any questions, feel free to leave them in the comments below, and I will answer your questions. Hope you found this useful. All channel members have access to a compiled executable of this program, but the source code is also open source and available at GitHub in the link in the video description. Until next time, thanks for watching, and clear skies.